أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم السلام عليكم ورحمة الله وبركاته.
وعليكم السلام
Walaikum assalam.
Thank
Walaikum
God
assalam.
for all His blessings and bounties that He has bestowed upon us. فَبِأَيِّ آلَاءِ رَبِّكُمَا تُكَذِّبَانِ comes in Hadith more or less meaning while talking to the companion of the Prophet sallallahu alaihi wasallam. It was asked, renew your iman. So how do we renew our iman? O Prophet of Allah sallallahu alaihi wasallam replied by the companions of the Prophet sallallahu alaihi wasallam. Then it was stated, say frequently, La ilaha illallah, there is none worthy of worship except Allah subhanahu wa ta'ala. So in order to get the real success of this life and the life hereafter, we need to follow the commandments of Allah subhanahu wa ta'ala, the way shown by the Prophet sallallahu alaihi wasallam. So inshallah, learning, talking and propagating it will be very, very beneficial for all of us. Today is 16th of December 2020 and we are going to talk about infinite sequences and series. In fact, today we are going to conclude this topic. We started off way back. While talking about sequences, initially got an idea what a sequence could be. And then we extended our journey while talking about a series. Plenty of options are there when we talk about the convergence or divergence of a particular series. Today, we are going to continue with that, exploring a couple of more options over there in order to see the convergence or divergence of a particular series. The first one that is going to be explored is the limit comparison test. If you remember in the last lecture, we got an idea how do we compare the provided series with another one. So based upon the convergence or divergence of an alternative series, we say something about the convergence or divergence of the given series. So that test is going to be different from the one we are going to talk about today. It is known as limit comparison test. So sort of limiting process to be considered while talking about the convergence or divergence. Again, sort of comparison over there. I mean, it is not the direct thing that we are going to take into consideration. If I remember, we discussed this one, I think, in the last lecture. If I remember, I think we discussed this one, isn't it?
Yes, sir.
All right. So we move on. Thank you. The ratio test. We got only one series with nth term to be labeled as an for all sort of values of n starting from 1. We say that if this series is of positive terms, means every term is going to have a positive value for all sort of values of n. You label them those terms as a1, a2, a3 up to an, and then so on. So if all the terms are of positive values, we say that the series is going to be positive term series. And on top of that, we are talking about the ratio. A ratio between the n plus 1th term and the provided nth term. So if the limiting value to that fraction is a, for example, we label it as L, is a non-negative real value, then what are the options to describe the convergence or divergence? The first thing, if that outcome is less than 1, we say that the given series is going to be convergent. We take the fraction between the nth term. Nth term will be provided to you, and we will generate n plus 1th term from the nth term. Take the fraction between them. On top of that, the limiting value to that fraction, if it is L, the outcome, L is non-negative real number. So if this value is less than 1, as an arbitrary value, we say that if it is less than 1, the series is going to be convergent. If this outcome is greater than 1 or infinity, the given series, that one is going to be divergent. So convergent in the case if the limiting value to that fraction is less than 1. Divergent if it is greater than 1 or of course infinity. And what happens if it is exactly equal to 1? We say that this test is going to be inconclusive. It won't say anything about the convergence or divergence. The test is going to be failed in this case. And it's a fundamental thing in the world that there is not a unique technique available for each and every type of phenomena. So we have plenty of techniques available. Some of them are suitable for certain cases and some others to other phenomena. So not necessarily that you have only one option that is going to be applicable to each and every option. So if the series is there and we apply the ratio test, the outcome is going to be exactly 1. We say that this test is going to be inconclusive. It won't say. It won't describe the convergence or divergence. Then you need to shift to an alternative option, as we do have plenty of options are there as an alternative option to test the convergence or divergence. When do we say that this test is going to be the most effective one? So we say that when the terms of a series contain factorials of expressions involving n. So the best of the option is there to look into the implementation of ratio test is that when the terms of a series contain factorials, or sometime we can also look into the expressions raised to a power involving n, but most of the time it is most effective against a series involving terms of a series, something like factorials over there. So much easier if you remember the definition of a factorial. You got nth factorial in the denominator, n plus 1th factorial in the numerator. So expand the factorial in the numerator. So you see that they are going to be cancelled out, the other part of the factorial in the numerator with the denominator. So this is how things are going to be much easier if the expression is there involving factorials over there. So best way to look into this test, the ratio test. We take a few examples from the exercise. Like in this example, Examples are there from 1 to 8 in this exercise number 10.5. Explicitly, it is mentioned that we need to apply the ratio test to determine if each series converges or diverges. So we need to observe the convergence or divergence of the given series by implementing the ratio test. You see that factorial is there. And the first example, factorial is there, factorial is there. So most of the time we see sort of factorial over there. So this is one of the best way. Other options are also there. We can implement the ratio test, but the best of the option is that when we have factorial in the expression of the nth term, so we look into the implementation of the ratio test. So we take an example. How do we look into the implementation of this test? So in order to look into the implementation, we need to go on the sideways board. So take a look at example number 1. So example number 1 is a series and varies from 1 to infinity with nth term is there. Two raised to power n upon n factorial. So this is how we have been given the nth term of the series. So if you merely label it as an, for example, then every term of the series is to be obtained from this nth term. So what would be the n plus 1th term? So simply by replacing n by n plus 1, it will be the n plus 1th term. So 2 raised to power n plus 1 upon n plus 1 factorial. So this is how we will be having the n plus 1th term. By the ratio test, we need to take a limiting value as n approaches to infinity to that fraction, a n plus 1 upon an. So this is the formula that we need to see as the implementation of this ratio test. Take the fraction between the n plus 1th and the nth term. So n plus 1th term is there as an expression, the nth term is there. We need to apply the limit to that fraction. So limit n approaches to infinity. So here you go with n plus 1th term. So 2 raised to power n plus 1 upon n plus 1 factorial divided by the nth term. So we have 2 raised to power n upon n factorial is the denominator. So play around, simplify that, limit n approaches to infinity. So this could also be written like 2 raised to power n plus 1 upon 2 raised to power n, and those factorials could be adjusted in that way, n factorial upon n plus 1 factorial. And if you remember the definition of n factorial, by taking a particular value of n, like 5 factorial is going to be 5 into 4 into 3 into 2 into 1. This is how the 5 factorial will be expanded, multiple of all those integer values. So it could also be written like 5 factorial could also be written like 5 into 4 factorial. sometime we can also look into those multiple values to be expressed in terms of factorial. For example, these values 4 times 3 into 2 into 1 to be labeled as 4 factorial. So 5 factorial could also be written as 5 into 4 factorial. Or another way to look into that, 5 factorial is equal to 5 into 5 minus 1 factorial. So pretty much on the same line, we have n factorial, we have n plus 1 factorial. So that n plus 1 factorial, like this one, could be written as n plus 1 times n factorial, just like this one. So n plus 1 factorial could also be written like n plus 1 times n factorial for our own convenience, because you need to combine them. N factorial is there in the numerator, so n plus 1 factorial could also be expressed like n plus 1 expanded with one more term. If you combine them, these two, they are going to be with the base, same base. If you take that factor in the numerator, so n plus 1 minus n, we're left with 2. And from these two, since the denominator is there, n plus 1 times n factorial, so that n factorial is going to be balanced out, and we left with n plus 1. So simplify that. Eventually, we left with that expression. 2 upon n plus 1, the most simplified expression. If you look into the fraction between the n plus 1th and the nth term, so the most simplified expression is going to be 2 upon n plus 1, and then apply the limit. So if you apply the limit, something finite upon infinity is going to be 0 as n approaches to infinity. So something finite upon infinity is going to be 0. So 0 is less than 1. What the idea of the implementation is that we need to see the limiting value to the fraction. The ratio is there between the n plus 1th and nth term. If the limiting value is less than 1, the given series is going to be convergent. If it is greater than 1 or infinity, divergent. Test is going to be inconclusive if the outcome is exactly equal to 1. So we say that since the limiting value is less than 1, so we say that the given series is going to be convergent. By the ratio test, the given series, that one, is a convergent series. So this is all. We look into the implementation. It's a matter of finding limit. We have gone through extensively with the topic of limit continuity at the start of the semester. So we just need to recall all the concepts from the topic of limit. So based upon the limiting value, we look into the outcome. So outcome is going to describe the convergence or divergence of the given series. If you look into example number 3, so factorial is there. No factorial is there. Even then, we can look into the outcome. The nth term is given. So look into the n plus 1th term from the given nth term, and then take the fraction, simplify the expression. And eventually, with the simplified expression, look into the limiting value. And based upon the limiting value, we will look into the outcome, whether the series is going to be convergent or divergent. So this is known as the ratio test. So examples are there from 1 to 8. You need to follow that. We move on to the last option to see the convergence or divergence, the root test. Pretty much like the ratio test is there, we have been given a series is there, which is a positive term series. Every term is going to be a positive value. And on top of that, if you look into the nth root of the nth term, 1 upon an raised to power 1 upon n means we are talking about the nth root of the nth term. And then on top of that, we apply the limit. N approaches to infinity. Since we are talking about the nth root of the nth term, so this is it is known as the root test. By taking the nth root to the nth term, and on top of that, the limiting value as n approaches to infinity, we say the outcome is going to be labeled as L, being a non-negative real number. If L is less than 1, just like in the previous case, the ratio test, the series is going to be convergent. If the outcome L, being a non-negative real number, is greater than 1 or infinity, that series is going to be divergent. And test is going to be failed. To say something about the convergence or divergence if L is exactly equal to 1. So those 3 criterions are identical to the previous test, the ratio test. The difference is there, now rather than taking the fraction, taking the ratio, we are talking about the nth root to the nth term. So based upon the nth root to the nth term, we look into the limiting value. So based upon the limiting value, we try to figure out whether the given series is going to be convergent or divergent. What is the practical implication? Where do we look into the implementation of the root test? So we see that it is going to be effective for series involving terms having exponents. When you have something raised to power, generally in terms of n, because of the nth term over there. So this is all to make things simple. We try to look into the root test. I mean, the nth term involves an expression of the form that you have something raised to power. Since it is not the nth term, so you are expecting that the power is going to be n. So in order to kill that, or in order to make things simple, we take the nth root. And this is all you see, the outcome is going to be simple. Once the expression is going to be simplified, we apply the limiting value to that simplified expression and then see the outcome. Based upon the outcome, we look into the convergence or divergence. So again, it's an option, not the ultimate option is there, because if L is equal to 1, the test is going to be failed. It is going to be inconclusive. So only we need to take the nth root and then the limiting value to the nth term. So take an example from 9 to 16. They're pretty much on the same line. So we need to figure out explicitly by implementing the root test to determine the convergence or divergence of the given series. So condition is that the series should be a positive term series. So we look into the implementation. Sometime we see that the criterion is not fulfilled. In that case, you need to look into the alternative option. If the criterion is fulfilled, yes, we are happy to apply that particular test. So the only requirement is there. We need to see if the terms are of positive term. So we see the implementation once more. We have to go on the board. All right, take a look at one of the example. So the series is given like in that example number 9, 7 upon 2n plus 5 raised to power n. This is the expression. So 7 upon 2n plus 5 raised to power n, and varies from 1 to infinity. So we need to see the convergence or divergence of that particular series based upon the root test. So if you label this one as an, the nth term, then you need to take the nth root of that nth term, and based upon the limiting value to that one, you need to see the convergence or divergence. I mean, what the test is here, we need to apply the limit n approaches to infinity to the nth root of the nth term. So that's what we need to do. So take limit n approaches to infinity. Nth term is there, 7 upon 2n plus 5 raised to power n. So we take nth root to that nth term, so 1 upon n. So implementing, we see that it will turn out to be n approaches to infinity, 7 raised to power 1 upon infinity. And in the denominator, you see that if you combine that 1 upon n with n, they are going to cancel out, and we left with 2n plus 5. So again, the simplified expression is there by taking the nth root. So apply the limit over there. So if you apply the limit, 0 is there, 7 raised to power 0 is 1. So finite value divided by infinity. So something finite upon infinity, again, it is going to be 0. And we know that 0 is less than 1. Since the limiting value is 0, which is less than 1, so the given series is going to be convergent. Based upon the root test, the nth root test says that the given series is going to be a convergent series. So again, it's a matter of finding limit. You need to recall all the concepts from the topic of limit. So based upon the limiting value to the nth root of the nth term, we talk about the convergence or divergence of the given series. Pretty much on the same line, you can try all these examples from 9 to 16. If we further look into the examples of this exercise number 10.5, there are plenty of examples are there. but I would say that you need to try up to 30, for example. From 17 to 30, for example, if you try these examples, what is the provision in this case from 17 onward? Use any method to determine if the series converges or diverges, but you need to give reason behind the scene. How would you justify the convergence or divergence, or which method is to be implemented? You need to justify that. The convergence or divergence of a particular series based upon a particular technique. So you need to illustrate that. Yes, by using, for example, the root test, or for example, the ratio test, the series is going to be convergent or divergent. So you need to give reason to your answer. Now, by the way, what are the options behind the scene if you talk about the convergence or divergence of a series? Remember, we have plenty. We started off with the idea of geometric series. The convergence and divergence of a geometric series is all based upon the common ratio. So if common ratio is less than 1, we say that the series, the corresponding geometric series is convergent, otherwise divergent. Then we have second option, the nth term divergence test. So based upon the limiting value to the nth term, I mean, if it is infinity, the outcome, or different from 0, we say that the given series is going to be divergent. It is known as nth term divergence test. Third one, we talk about P series based upon the value of P. We talk about the convergence or divergence. I mean, if you have the nth term, something like 1 upon n raised to power P. So we talk about the convergence or divergence. If P is greater than 1, the series is going to be convergent. Otherwise, it will be divergent. If P is less than or equal to 1, the series is going to be divergent. Then we talk about the Cauchy's integral test based upon the integral. We look into the convergence or divergence. We discussed about the comparison test, the basic comparison test. Then we discussed about the limit comparison test. And today we have discussed a couple of more options. The ratio test and the final one, the root test. So based upon those options, you have liberty to apply any one of them. So you need to figure out yourself which one is more applicable to certain examples. I mean, we have tried our level best to see which one is more applicable to certain cases, like the root test, when the expressions involving something raised to power, involving exponents. The ratio test is there when factorials are there. So you need to figure out them. Look into the theory, the theoretical aspect, and then see the most appropriate option. You have plenty to apply. All right, in the next 10 minutes or so, I would like you people to see, before we move on to the next topic, if there is any query about the limit, the sequences and series, in particular about today's lecture, from example number 1 to 30, or from the previous one, so we can discuss as we got some time. So have a look at those examples. And in a 10 minutes or so, in a time of that, we will look into a new topic, inshallah. So in the meanwhile, I mark your attendance as well. All right, so we move on to the next topic. Effectively, it's not a comprehensive topic. Like if you look into the contents again, there are mainly three parts over there. The first paragraph is about the differentiation and its applications. So plenty of them. We discussed them extensively. The topic left in the first part is to discuss Taylor series, a very, very vital thing to be discussed. Taylor series is basically regarded as the backbone of applied mathematics. Because whenever we look into the development, whenever we look into the construction of a new numerical technique, it all based upon the Taylor series expansion. We need to compare the order of the method. We also need to look into the error produced by that method. It is all based upon the Taylor series expansion. So this is how we say that it is going to be one of the most vital thing to be discussed. Newton's method is going to be another vital option to be discussed when we talk about the root of a non-linear equation. Single non-linear equation is there. So equation in the form of algebraic expression is there. So algebraic equation will be there. I mean, it is not going to be a differential equation, remember, not an integral equation. Algebraic equation, simple algebraic equation is there, but non-linear. And we are interested to find its root. So these are the things we need to talk about before we talk about one of the other heavy hitting idea in this particular course, to talk about integration and its applications. So we need to cover them. Today we are going to talk about the foundation of this topic. Before we talk about general theorems, we take start from approximating functions. We are going to talk about the approximation. Remember, there are many Do you want to say something? 78. Try to mute your microphone until you are told to do so. All right. So we are going to go with the approximation. We are going to get an approximate value of a function based upon the piece of information at your disposal. In applied mathematics, we frequently deal with the problem of approximating a function at a point or over an interval, or the problem of approximating the exact solution of an equation. So remember, the word approximation will take us to numerical value. There are plenty of ways we can describe this thing. Sometimes it is labeled or it is elaborated as approximate value, numerical value, or numerically approximated value. To the other end, we will be having terminologies like true value, exact value, or analytical value. So we are going to talk about approximate value now. Approximation means numerical value. So here we consider the case where we know the value of a function and its derivatives at only one point. What do we know about the value of the function at a neighboring point in the neighborhood of that particular point? We have the piece of information at a specific point, but how do you approximate the value of the function in the neighborhood? There are infinitely many options. How do you approximate the value of the function in the neighborhood? So we have been given the piece of information at one point. What are those information? For example, we know the value of the function. We know its first derivative, its second derivative, its third derivative, and then so on. So either we are interested to utilize the value of the function alone, or we are interested to utilize the value of the function and its first derivative, or another option is there, we are interested to utilize the value of the function, its first derivative and second derivative as well. So it depends upon the piece of information that you take into consideration. We will see how the approximation is going to go with the accuracy, the observed accuracy. So we'll try to figure out, based upon those information, how do you approximate the value of the function in the neighborhood? So we start from the point that we have piece of information at a particular point. So again, we need to go on the board. So I try to figure out what do we have and what are we interested for. So initially we start off with the point that in the XY plane, we all know the baseline is A, the x-axis line. The interval is always going to vary along this line, whereas the value of the dependent variable is going to change alongside this vertical line. So we say that, okay, for example, this is going to be the behavior of the function described by this outline. And at a specific point, for example, that one, we have the piece of information. What are those pieces of information? Because remember, the function is there along the line y-axis. X is there along the line x-axis, and y means y is equal to f of x is there. What are the information we have? We have the value of the function. We have its first derivative. We have its second derivative. We have its third derivative, and then so on. All these values are available at a specific point for certain value of x. If you label it on the horizontal line, mark it somewhere over here. So corresponding to that value, we have the value of the function, its first derivative, second derivative, third derivative, and then so on. What are we interested for? We are looking to approximate the value of the function in the neighborhood somewhere. I mean, if you are traveling towards the right hand side, this is the next value. To the left hand side, for example, over here. So we are interested for the approximation in the neighborhood. So in the neighborhood, we are interested to see how do we approximate the value of the function. One of the options is there, just utilizing the value of the function. We look into the value of the function in the neighborhood, or we are interested to utilize these two pieces of information. We utilize the value of the function at a specific point and its first derivative, and then approximate the function in the neighborhood. Or another option is there, we not only utilize the value of the function, its first derivative, but also we utilize the second derivative. With these three information, we approximate the function in the neighborhood. Or we utilize one more derivative and then so on. How the numerical approximation is going to behave in terms of accuracy based upon the piece of information that are going to be utilized. But before we move on, have a look at those derivatives. We all know about the first derivative, f prime. F prime is going to describe the behavior of a function. I mean, if you are interested to see whether the function is going to be increasing or decreasing, we need to observe the sign of the first derivative. Based upon the sign of the first derivative, we can observe the behavior of the function to be increasing or decreasing. So one of the most prominent application of the first derivative is to observe the behavior of the function. Remember from the previous lectures, if the sign of the first derivative is positive, we say that the function is going to be increasing. If the sign of the first derivative is negative, we know that the function, the corresponding portion of the graph is said to be decreasing. Increasing behavior is going to be described by that one, and decreasing behavior is going to be described by that one geometrically. I mean, the best way to describe that, as you increase the value of x, the value of the function is going to be decreased. But in this case, as you increase the value of x, the corresponding value of the function is to be increased. So in other words, we say that for increasing behavior, x and f of x are directly proportional to each other. For decreasing behavior, x and f of x are going to be inversely proportional to each other. And when we talk about the application of second derivative, one of the most prominent application is concavity, second derivative. I mean, if second derivative is positive, we say that the corresponding behavior of the function is such that it is going to be concave up. I mean, this is the portion of the graph to be called as concave up. I mean, faces upward, just like that. Vertical parabola is it. With endpoints, the faces are in the upward direction. So it is known as concave up. Concave up. So second derivative will take us to concavity. If the sign of the second derivative is positive, we will be having a behavior of the function that is going to be concave up. In the case second derivative is negative, we will be having concave down. The sign of the second derivative is negative. So this is how we can look into those. The first derivative, the function is going to increase or decrease based upon the value of the first derivative, positive or negative, or it is going to be concave up or down based upon the sign of the second derivative. Just to recall those concepts from the previous lectures. So what if you utilize the value of the function? How good our approximation is, or not only the value of the function, but also this behavior, either this one or that one. If you add this one, how good our approximation is, or if you add one more derivative over there. So we know the practical implication of the second derivative. So we are trying to figure out. Have a look. Idea is that we are interested to see the value of the function in the neighborhood by utilizing certain piece of information. What the information do we have? We have plenty. We have the value of the function, its first derivative, second derivative, third derivative, and then so on. At one value of the function, at one value of x, we have plenty of information. So how do you approximate it in the neighborhood by utilizing certain piece of information? So take a look at the next graph. So assume that we got a nice graph of the curve. Y is equal to f of x. And for example, corresponding to x naught, the value of the function is there, f of x naught. So this is the value of the function. Corresponding to x naught plus h. For example, we label it over here. We travel by some amount, for example, h units towards the right hand side. So corresponding to x naught plus h, normally you can also label it like x1. We travel over the interval with length of the interval h units from x naught to x1. What is x1? It's basically x naught plus some increment h units. Corresponding to x1 or x naught plus h, the value of the function is somewhere there. This is the true curve y is equal to f of x. So the value of the function would be f of x naught plus h. So these are the true values of the function corresponding to x naught and x naught plus h. So these are the values. So we are going to approximate the value of the function, for example, corresponding to x1 by utilizing the value of the function only, for example. So then what will happen? We need to follow that horizontal dash line. I mean, if you do utilize this value, we know that it is going to be a constant value corresponding to x naught. F of x naught is going to be a certain value, constant value is it. That constant value is going to be fixed, whatever the change that you make in the value of x. I mean, no matter whether you change x naught to x1 to x2, x3, whatever it is, the value of the function is going to be unchanged because it is going to be certain value, fixed values there. So we say that if you approximate the function corresponding to the value of the function, you will end up somewhere there. So this is the value of the function in the neighborhood at x1. But the exact value is there. Exact value is far away from here. So exact value is there. But now the approximate value is there. How do you approximate this value? By utilizing the value of the function only, by forming this horizontal dash line. So you will end up over here. So you see that this is going to be the difference between the exact value and the approximated value, which is going to be labeled as error. Error is going to be described at the highest at the advanced level. Normally, you will talk about that in the course of numerical analysis. Performing those extensive numerical testing, you need to talk about error. Simply, what do we say about error at this point in time? The difference between the exact and the approximate value. Exact value is there, and here you go with the approximate value. So the difference between the exact and approximate value is going to be labeled as error. Plenty of types are there of error. Error in position, error in velocity, absolute error is there, relative error is there, percentage error is there, global error is there, local error is there. So plenty of types of the errors are there. But anyway, just take a glimpse of idea behind the scene while talking about the error. Difference between the exact and approximate value. So we say that if you just utilize the value of the function is available at x naught, f of x naught is there, and we utilize this value to approximate the function in the neighborhood, for example, corresponding to x1. So what will be the outcome? This approximation says that our value corresponding to x1 will be that one. And if you label it on the vertical line, it will be marked somewhere here. But the exact value is here. So it is going to be a big difference between the exact value and approximated value. So we say that this approximation is not going to be so good because there is going to be big error. Now what if you add one more piece of information? I mean, we follow that inclined line, that one. The dashed line is there, but it is going to be inclined, for example. How do you approximate the value of the function in the neighborhood? Not only by utilizing the value of the function, but also its derivative. What the derivative is there, the rate of change. So we follow this tangent line, basically, this dashed tangent line. What are the information that we need to take into consideration? Why will be obtained? Why is basically the outcome corresponding to the value of x in the neighborhood of x naught? So not only the value of the function, but also we utilize its derivative at x naught. The value of the function is utilized and its first derivative is to be utilized, but over the interval from x to x naught to x basically. And if you, for example, it's an arbitrary value, x, but if you take x is equal to x1, for example, so in this case, that expression would be f of x naught plus, so if you replace this one by x naught plus h, so x naught will cancel out, you will left with h. So you will be having an expression like h times f of x naught. So this is how the next approximation will be obtained. So that line is basically the linear approximation. We utilize the value of the function, its first derivative, over the step being taken to travel from x naught to x1. So we are interested to figure out the value of the function in the neighborhood by taking a step size of h units, that much. But now you see that, I mean, the message is that if you look into the approximation by forming that tangent line, so our approximation would be somewhere here. The approximate value of the function by utilizing not only the value of the function, but also its first derivative, our approximation would be somewhere there. So now it's much closer to the exact value in comparison of that one. Initially, if you just utilize the value of the function, we end up over there as an approximate value, but it is not going to be as good as that approximation is there when we not only utilize the value of the function, but also its first derivative, step size is there. So we see that we have better approximation if you not only utilize the value of the function, but also its first derivative. What if you add one more term over there? Not only the value of the function, its first derivative, if you add one more term, we are expecting that we are getting closer and closer to the exact value as you add more derivatives over there. As you add more piece of information over there. And that's what is the message behind the scene. The message is there before we talk about the Taylor series expansion, because there are going to be finally many terms over there in the Taylor series expansion. We see that if you are interested to approximate the value of the function in the neighborhood of the standing position, whatever the standing position is there, if you are going to approximate this one in the neighborhood, so based upon the piece of information, if you are just interested to utilize the value of the function, the approximate value can be obtained, but this is not going to be an acceptable option, as we have seen geometrically, that the error is going to be significant in that particular case. But if you add one more piece of information on top of the value of the function, the derivative, combine them, it will turn out to be tangent line. So you will see that, yes, now the approximation is far better than the previous one. So pretty much on the same line, if you extend the journey, add one more piece of information like the second derivative term, add one more piece of information, the third derivative term. So as you increase the piece of information, as you involve more derivative terms over there, so we are expecting to get better and better approximation. That's the message is there. So take a look at the description. So there are two figures, remember. The first figure is that one. We say that we have piece of information when we know the value of the function and its derivatives at only one point. What do we know about the value of the function at a neighboring point? We are interested to approximate the value of the function in the neighborhood. So how we do that? So this is all we look into the second figure. The second figure where we have the exact curve is there like this one. And we are going to approximate this one by dashed horizontal line or a dashed tangent line. We are going to approximate this one. So we take start from here. We specify the problem as we know the value of the function, its first derivative, second derivative at a specific point like x naught. And we are interested to estimate, we are interested to approximate the value of the function at a neighboring point, for example, x naught plus h. You can also label it as x1, for example. By traveling a distance of h units along the line x-axis from the standing position. The standing position is x naught, and the next value is going to be x1 from the standing position. We are interested to observe the value of the function corresponding to the later state. The later state is going to be there by looking into the standing position plus some increment. So this is how you talk about the neighboring point and the neighborhood of the standing point. So two initial approximations to the function at x naught plus h, that is f of x naught plus h. are shown in the figure. I mean, the first one is the horizontal dashed line, y is equal to f of x naught. It is not going to be a satisfactory approximation. Approximation to the value of the function against x naught plus h. So we are interested to figure out the value of the function corresponding to x naught plus h. Exact value is a, the curve is a, the exact value. And we approximate it by the value of the function only. And we see that at the end of the day, there is a big difference between the exact and the approximated value. So we say that it is not going to be a satisfactory approximation. But if you follow the dashed tangent line, how do you see the tangent line? Not only the value of the function, but also its first derivative is involved. Over a specific interval, x minus x naught, I mean, specify x as x naught plus h. So if you place x by x naught plus h over here, x naught will cancel out, you will be left with h. So it is going to be something like f of x naught plus h times f prime of x naught. So this approximation is called as the linear approximation at x naught plus h. And we have seen that it is going to be good in comparison of the dashed horizontal line. Dashed horizontal line is not going to be a satisfactory approximation. But now if you add one more piece of information, the derivative. So derivative term is there. So we see that yes, we are getting closer to the exact value. So how good is this approximation? It's a technical thing. We need to take into consideration many of the things from the assumed knowledge. Of course, at this level, we are not going to talk about all those aspects which are essential to talk about the level of accuracy. Of course, you need to talk about them at the level like talking about the numerical analysis course or numerical methods. I presume that you will talk about them in the fourth semester. Fourth or sixth semester. I'm not sure, but it will be there in the upcoming year. So you extensively talk about those technical terminologies over there. For the time being, we're just interested to see the glimpse of idea. So the message behind the scene, as you increase more piece of information, we are expecting better and better approximation. If the derivatives of a function exist up to nth order, then the nth degree polynomial constructed in this way is called Taylor polynomial of degree n, and it is given by that. I mean, either you are interested to cut it down up to only one term, this is one of the approximation, or you take one more piece of information, not only the value of the function, but also its derivative. So you need to figure out these two terms, or you add one more term. So you will be having this expression. You need to simplify this one to get a different approximation, different from the previous two, and so on. If you add n terms over there, for example, so you need to provide all sort of piece of information. So we are expecting that as you add more piece of information, you are getting better and better approximation. And the piece of information in terms of derivatives, the value of the function, that's first derivative, then you involve one more term with second derivative, one more term with third derivative, one more term with fourth derivative, and then so on. The Taylor polynomial for f of x about x naught is used to approximate the value of the function at points in the neighborhood of this one. It's what we discussed at x naught plus h, in the neighborhood of this standing position. So this polynomial is basically utilized. And pretty much on the same line, the idea is here of Taylor series expansion. We will look into the Taylor series expansion in the next lecture, inshallah. All right, so that's it for today's lecture. In this lecture, we have concluded the topic of infinite sequences and series. And we also